Okay, welcome once again. Chemistry 3202 review. This is going to be standard reduction potentials, the standard reduction table, Unit 4, Section 2, Lesson 2. Now, if you haven't already done so, what you should do is go to the table and charts link in the content link and print off the standard reduction table. We're going to be looking at that one in a little bit of detail in this lesson, so we'll make sure you go get that one. So you might want to pause this, go get that table, print it off, and when you're ready, resume the lesson. So here we go. Okay, we're looking at the standard reduction potential, and what we're referring to is the standard hydrogen electrode, or SHE. That's what we're going to refer to it as. And in your textbook, you can look at some background information here, page 761. And there's a few extra little practice problems here you can have a look at as well. So here we go. Okay, here are the outcomes for this lesson. Okay, now we're looking at this idea of potential energy for the most part. And we looked at this in several different ways throughout this course, from the enthalpy in terms of the stored potential energy in bonds, the internal energy that's being stored. What we want to do here now is we want to look at redox from a potential, from a perspective of potential energy. And what we're looking at is the idea that if we can take different types of metals, for instance, zinc is a very reactive metal. So in terms of its position with respect to other metals, it's going to be relatively high on the mountain range here, I guess. It's going to have very high potential. Metals like zinc and magnesium and things like that, very chemically reactive. If we take some zinc and drop it in hydrochloric acid, you know, almost instantly we start to see hydrogen gas being produced here. So very chemically reactive. Where if we take some other types of metals, they don't react as fast and whatnot. So the reactivity series is there. Zinc is very reactive. Now if we compare that to, say, copper, now we did this in a half cell in the last lesson where we had zinc and copper. Zinc electrode was in one test tube and copper was in the other test tube. And we said that the electrons were going to flow from the zinc to the copper. So in that case, the zinc was acting as the anode. The zinc was being oxidized. So we could say then that the electrons were flowing to the copper. So in this sense, we said that the zinc, because it was more reactive, it was easier to oxidize, was going to be represented by the oxidation reaction. And at the same time, because we had copper placed in a container of its own ions, what we said happened here was that the copper ions that was in the container was accepting these electrons from the zinc to produce copper metal. And we said no matter how many times we put these combinations together, zinc and copper, the electrons will always go spontaneously from zinc to copper because zinc is the most reactive metal. All right, now if we looked at some other types of metals and said, okay, well, where would we put cadmium if cadmium was placed here? And we can look at this and we said, well, if we put cadmium in here, cadmium is somewhere in between copper and zinc. So if we had zinc and cadmium, zinc in one test tube or one beaker, piece of zinc metal and zinc ions, and then another test tube or beaker with cadmium metal and cadmium ions, what we're going to find is that zinc is going to be positioned above the cadmium as well. So in this case, the zinc is still going to be oxidized because zinc is more chemically reactive than cadmium. So zinc will be oxidized. The cadmium will be reduced. Okay? Now if we changed it up a bit and we said, hold on now, let's get rid of the zinc. And let's do a combination where we had cadmium metal in one container in its ions, and we had copper metal in another container in its ions. And what we're going to find here is that because cadmium is positioned higher than copper, that the electrons are going to flow from cadmium to the copper because cadmium is more chemically reactive. And likewise, we can start looking at all the different types of combinations that we can come up with. So if we say, okay, let's use gold this time. Let's use gold in its ions as one of the electrodes, and then we'll compare it to zinc, and then we'll compare it to copper, and then we'll compare it to cadmium. And what we're going to find out is that, hey, well, gold is pretty much stable for the most part. It's pretty much unreactive. But when we mix it with a zinc electrode, the electrons will definitely go from zinc to the gold ions. So in this particular combination, the gold is going to be reduced instead of the zinc again. So zinc is always the most reactive metal of the ones listed here. So the electrons are always going to fall from zinc to gold, from zinc to copper, from zinc to cadmium. Likewise, if we had to do a combination of, say, copper and gold, well, even though copper is less reactive than zinc and cadmium, it's more reactive than gold. So therefore, copper would be the easier one to easier to oxidize than gold. So what we're seeing is that the electrons are always falling or being oxidized from the metal that's more reactive to the metal that's least reactive. So depending on what combinations we have there, we can start ranking all of these different combinations according to their potential for oxidation or their potential for reduction. So what I've got done here is I've simply put a little curve here, a little axis, X and Y axis, saying, okay, this guy is going to be of a higher potential than cadmium. Okay, and then copper would be of a higher potential than gold, and it would fit down like this. So we would see zinc, then cadmium, then copper, and then gold. And I'll just move the gold down there. There we go. Now, we want to be able to put a value on this potential difference. We want to be able to say, well, can we measure that difference between zinc and copper, and what's that number going to be in terms of electrons being moved? All right, and what we do here is we say, okay, if that electron is moving, we can harness it in our electrochemical cell because we can have that piece of wire connecting the two electrodes together. We have our salt bridge to control the flow of ions. So if we could harness that electron going through the electrical wire, and that electron is doing work for us, turning on light bulbs, turning on electric motors, turning on an iPod, we should be able to measure the voltage or the amount of energy that that electron has. Get it? So the potential difference between zinc and copper is going to be the energy that the electron has as it falls from zinc to the copper ions. So it's going to be, this is going to be our electrical potential energy. And we measure electrical potential energy by way of voltage. Okay, something that has more electrical potential is going to have a higher voltage difference. And what we mean by a voltage difference is the difference between where the electrons are going. So the difference between zinc and copper is going to be a much larger voltage than the difference between zinc and cadmium. There we go. Okay, now we want to be a little bit more accurate than that. So we want to be able to measure the electrical potential difference or the electrical potential of a cell. And we're going to give it the symbol E. Okay, so electrical potential is called E. It's measured in volts. And sometimes we simply call it the cell voltage or the cell potential, okay, because it's not going to do any work, of course, until we close the switch. The electrons are not going to be able to flow within our cell until we close the switch. And if a cell potential has a 0 voltage, that means the electrons are not able to do any work, right? We're at the same level. So if two metals happen to be ranked at the same level, then the electrons are not going to be able to fall. So if I had another metal here that was very similar to cadmium at the same level, and I had those two hooked up, it's not going to be able to do any work because the electrons don't have anywhere to fall. There's no potential difference. So if we have the same metals hooked up, so let's say we had a zinc electrode connected with another zinc electrode, well, they're at the same height, so they're not going to produce any voltage because they're at the exact same energy, and the electrons are not going to fall from one to the other because neither of them are higher. So in this case, if we're going to create a cell, we must have different reactions happening in each electrode. Okay? So there we go. Now we want to be able to measure this very accurately. So we have to create some kind of reference point. And our reference point is going to be what's called the standard hydrogen electrode, SHE, standard hydrogen electrode. Now because we said standard, we want to stipulate, well, what are the conditions? We just can't willy-nilly put this together and expect to get some good results. We want to be able to say, okay, we want accurate measurements. We have to have specific standards. Everything has to be perfect if we're going to get some good measurements here. So the standard conditions is representing SATP conditions, standard ambient temperature and pressure. And that would be the surrounding temperature, room temperature, roughly 25 degrees Celsius, regular sea level atmospheric pressure, 100 kilopascals. And we're going to be pumping some hydrogen gas into our upside down test tube here. So the hydrogen gas gets pumped in and bubbles out. We're going to have an inert platinum electrode. Okay, inert platinum electrode, because we don't want the platinum electrode to be involved in the chemical reaction. What we want here is the hydrogen in contact with the platinum electrode producing hydrogen ions or acidic ions. And in this case, we might want to reverse the reaction, so we want to have some standard concentrations here. So anytime we refer to a standard electrode, the concentration is always going to be 1 mole per liter. So in this case, we've got zinc immersed in zinc ions. The concentration of the zinc ions are going to be a standard 1 mole per liter. Okay, so that's what we mean by standard conditions. And when we hook this guy up to, say, the zinc electrode, and we have a voltmeter here, the voltage reading we get is going to be a plus 0.76 volts. Okay, so that's the voltage reading we get. So we say, well, why do we want to use the standard hydrogen electrode, and what does that 0.76 volts refer to? Well, I'm going to go back here a second, and I'm going to say the standard hydrogen electrode is basically offering me a reference point. It's kind of like sea level, and I had this discussion once before when we talked about the standard molar enthalpies of formation. Remember, we said we had to pick something to be our zero reference point. Everything else is going to be compared to that point. In the standard molar enthalpies of formation, we said, okay, the easiest thing we can pick to have a zero enthalpy was the elements, right? Every element on the periodic table had an enthalpy of 0, and we compared everything to it. Did that necessarily mean that it had a potential of 0 energy stored? Absolutely not. We're simply saying that's our reference point. So in this particular example, or this particular situation, we're representing the standard hydrogen electrode. We're saying, okay, let's give that one 0 volts, because it's easy to produce and the conditions are easy to mimic. Anywhere in any lab we can easily create a standard hydrogen electrode. So let's call that 0 volts, and everything else is going to be compared to it. So if you have a greater potential than the standard hydrogen electrode, you're going to be above it. And if you have a potential that's less than the standard hydrogen electrode, you're going to be below it. All right? So this is going to be our sea level. So you can always be above sea level on the top of a mountain, or you can be below sea level and go down in the ocean somewhere. So we're always going to have this above and below our easily produced reference point. So it's just like sea level when we measure altitude. So when we look at this, we're saying, okay, if we're saying that zinc has a higher energy than the standard hydrogen electrode, and we're showing you that the zinc is going to be oxidized, we can now write this as a half-cell reaction and say, okay, if the zinc is being oxidized to produce electrons, and we know that because the electrons are being produced on the zinc electrode, if we can measure this to be a negative because this is going to be the anode. So that's going to have a negative. This is going to be the anode. All right, so we're saying, well, why then is it a positive charge that we're seeing up top? Well, because this is being oxidized, what we do is the table is a reduction table. So every value that's going to be shown on your table that we're going to write is going to be for reduction. And in this case, we have zinc being oxidized. So because we have the reverse of reduction, we're going to write this as a positive voltage. But on our table, when we change this around to represent it as reduction, it's going to have a negative value because it's reversed. So in this case, in this setup, the zinc is being oxidized. It's the site of oxidation. So we say that it's going to have a positive voltage here, but when we put it in our table, we reverse it. So what's going on then in the standard hydrogen table? Well, what's going on in the standard hydrogen cell here is that we have to have reduction. So reduction in this cell is going to be the reduction of the acid to produce hydrogen gas. So we're going to see the production of more hydrogen gas. If I could turn off this valve right here, I'm going to shut that down. This is going to occur because what's going to happen is as the electrons come through here, they're going to come in contact with the platinum, and the acid that's present is going to be reduced to produce hydrogen gas. So if I shut down the production of hydrogen gas here, we're still going to see hydrogen bubbling off. All right? And the voltage we get here is what we see in our volts meter, 0.76 volts for this chemical reaction. All right, so what we're going to do here now is we're going to say, all right, let's keep the standard hydrogen electrode here. Let's change this to copper in copper ions, get a reading. Let's put in a piece of gold in gold solution, get a reading. Cadmium in cadmium, you see what I'm doing? What we're doing is we're going to compare every single possible half reaction that we can do, and we're going to hook it up to the standard hydrogen electrode and see where they're positioned. Now, the only thing is, when we do this, we end up getting this lovely table that you guys should have printed off by now, and you can see that gold is way up here, and zinc is way down here. And we're saying, well, I thought you said zinc had a higher energy than gold. We do. The table's upside down. All right? So if you could take this table and look at it on this side only, and turn it upside down and say, okay, flip this upside down, zinc is definitely higher than gold now. Zinc is higher than tin, lead. Zinc is higher than copper. So what they've got done on the table is they're saying, okay, this is the increasing strength of reducing agent. Now what I like to say is that the zinc is easier to oxidize. So that's why it's down here on the table, way down low. It's the strongest one, it's the easiest one to oxidize, it's the most reactive. Magnesium is even more reactive than zinc. Lithium, barium, calcium, more reactive again. So down here on your table, if you've printed off the right table, you can see that on the bottom it says the easiest one to oxidize, which means that's the strongest reducing agent. Because remember, a reducing agent is something that's going to give up electrons. It's the one that gets oxidized. So in other words, the zinc gives up electrons more easily than, say, cadmium or copper, right there. On the top of this, we're saying, okay, these guys are the ones that are difficult to oxidize. So things like fluoride ion and chloride ions and these guys, once they have their electrons, they don't want to give them up. So they're very difficult to oxidize, so they're the least reactive on this side of the table. And you can see that gold is way up here. Gold is pretty much, doesn't really want to give up its electrons. And that's a good thing that gold doesn't get oxidized, because we make things like, it's a precious metal. We make jewelry. If your mom had a wedding band and she'd done the dishes and whatnot, or your dad or whatever, and they put their hand down in the soapy water and there was some other type of metal there, it wouldn't be very nice if they pulled their hand out of the dishwasher and their gold ring was oxidized. That wouldn't work nicely, would it? So gold is relatively inert for the most part. It really doesn't want to be oxidized, and it's very, very unreactive. So in a sense, we can rank it from the least reactive on this side of the table way down to the most reactive, which is the easiest to oxidize. All right? And if you look at the zinc electrode here, you notice how the sign is going to be a negative. So let me just increase the size of this. Okay. So the zinc electrode here is a negative 0.76. Now, when we hooked it up to the standard hydrogen electrode, it ended up being a plus 0.76. But don't forget now, when it was hooked up to the standard hydrogen electrode, this guy was being oxidized. In this table, it's showing me reduction equations only. All right? So this is a table of standard reduction potentials only. Now, we can also look at this table from a reduction perspective. So we can say, well, some things are easy to oxidize, while other things are very easy to reduce. So we look at this and we'll say, okay, the most reactive or easiest to reduce are the ones on top on this side. So something like fluorine really wants to accept electrons. It would love no more than to get a couple of electrons here to produce fluoride ions. So very, very chemically reactive, the fluorine atom, but the fluoride ion is pretty much unreactive. Okay, and we can put this in perspective if you want. Let me just get a new screen here. We can put this in a little bit of perspective where we can say, if we could do a fluorine atom, here it is with its 7 electrons. It's group 7 on the periodic table. It needs to pick up 1 electron to become fluoride ion. Here it's got an octet of electrons. Once it gets that octet, it really, really doesn't want to go backwards because now it's pretty much stable in the ion form. So if we could look at this from an equilibrium perspective, this equilibrium is going to lie far, far, far to the right. Because once this guy, this fluorine, has an electronegativity of 4.0, it has a very strong attraction for electrons. So this guy is going to attract that electron from whatever can give it to it. So it's going to be very, very easy to reduce this because it has that strong desire to get that one electron. Once it has these 8 electrons, its desire to be oxidized, to go back, not going to want to, right? So this fluoride ion is unreactive. It's pretty stable in this format. This fluorine atom is very chemically reactive. It's not stable. It wants to pick up an electron. So that's why this guy is easy to reduce. And this guy over here is difficult to oxidize. Okay? Now at the other extreme, down on the bottom of the table, we can have a lithium, piece of lithium metal. Now lithium metal has 1 electron. It's in group 1. So if you look at the electron distribution of lithium, it's going to be okay, three protons here, and it's going to have 2 and 1. So lithium really wants to get rid of that electron. So lithium would prefer to be oxidized to produce that 1 electron and a lithium ion, because the electronegativity of lithium is really low. It's 0.9. On your periodic table, it's actually 1.0. So it's really relatively weak. It wants to get rid of that electron because it wants to have the configuration of helium. It wants to get that noble gas configuration. So lithium atom has a strong desire to be oxidized. But yet the lithium ion is very difficult to reduce. Once it gives up its electron, it's not going to want to pick up. It doesn't want to go back. This is very chemically reactive. This is stable because now it looks like helium. So in terms of its position on the table, this is difficult to reduce, but this guy over here is easy to oxidize. And if we look at their position on the table, we can see that there's, as we go up here, it gets easier to reduce, and as we go down on the other side of the table, it gets easy to oxidize. Okay? So this reaction pretty much doesn't want to go forward. It will if we force it to, but under normal conditions it would rather not. Okay? So that's how the table is set up here, and everything is written with respect to reduction. Okay? Even though that this equation down here would rather not be reduced, we're going to write it as reduction, and we're going to put in our value for our voltage in terms of a reduction equation. So if we go back here, we can see that there's a ranking on both sides of this table in terms of oxidation and reduction. Okay? And every single one of these values is listed. And in terms of us doing our mountain range analogy, if I'm going to look at that side of the table only in terms of the ease of oxidation, the most reactive is on the bottom here, right? Aluminum, magnesium, lithium. These guys are very, very chemically reactive, very, very easy to oxidize. These guys up here are very difficult, lower energy. Okay, so let's go have a look at some questions now that can come up with this. And we want to be able to do a calculation for this as well. Okay, so what we're saying here is just a quick overview. We're saying that these values are standard. Everything has to be at 25 degrees Celsius and 101 kilopascals, and all ions have to be 1 mole per liter. That's standard conditions. And we just talked about the strongest reducing agent and the strongest oxidizing agent. The strongest oxidizing agent is easiest to reduce. Okay, and the strongest reducing agent is the easiest to oxidize. Okay, there we go. So important to have that table handy. Okay, you can mark it up if you like. I have one there with markings on it, so let's have a look at it. All right, so we want to be able to take this and say, okay, well, all right, enough of the standard hydrogen electrode. That's purpose was to try and establish that table, to rank everything according to how it fits with respect to the standard hydrogen electrode. We want to be able to look at this and say, well, what if I hook up some other electrode to say zinc? So in the example that we've done with the zinc and the copper, we want to look at this and say, okay, what's going to be the voltage? And we're saying that in terms of zinc and copper, zinc is always going to be the anode because zinc is the easiest to oxidize. It's easier to oxidize than copper. So let's go back to our table and put this in perspective. Okay, and I'm just going to zoom this up a little bit. And okay, there we go. So in terms of what's going on with zinc and copper, I'm looking at the position of zinc and copper on the table. And I'm looking at this, I'm saying, well, there's copper and there's zinc. Now, if the electrons had a choice between zinc and copper, which one would give up their electrons the easiest? Well, remember, as you move down this table on this side, it's getting easier and easier to oxidize. So what's going to happen is because zinc is lower than copper, the electrons are always going to flow from the zinc to the copper. And that's going to be our little statement right here that I've got written on your table. In electrochemical cells, the cathode, the one that gets reduced, is going to be higher on the table. The anode is the one that's easiest to oxidize. So the anode is going to be the one that's down low here. So in this case, zinc is going to be oxidized. So I have to flip this equation around. This is going to be my anode, the site of oxidation. So I'd have to flip this equation. This is going to be my reduction equation, so I keep it as it is. So let's go and do the calculations that go along with this. And we can look at this and say, okay, our shorthand notation is always showing the anode on this side, and this is on the right-hand side is always going to be the cathode. So it's written properly because zinc is going to be the site that's going to be oxidized. Okay, so when we do this, we're simply going to look their values up on the table. And the table values here for each of these, you notice I haven't changed the sign here, have I? I simply took them as they are from the table. And what we want to be able to measure in order to get the voltage, we want to be able to measure the voltage difference between the copper and the zinc. So this is the voltage that we're going to get. You know, where are we starting? Where are we finishing? So whatever that difference is, that's going to be our voltage. Okay, I got some difficulty with the pages here. Okay, so there's a formula that we can use then to calculate this, and the formula is always going to be, no matter what type of cell we're going to be using, it's always going to be E for the cell is equal to the E of the cathode minus E of the anode. And we're going to take these values straight from the table. Do not change the sign or anything like that. Just use the values straight from the table. So in this case, we've established what the cathode is. It's the copper half cell. So that value comes from the table, plus 0.34 volts, minus the anode. And the anode is the value for zinc right from the table, negative 0.76. Now, the sign negative right here is taking into account that even though this is a reduction value, we would have had to reverse the equation, but we don't have to worry about that because this formula takes care of that for us. So this negative sign is going to change the sign inside here, which now puts everything in order for us. So we figure out what the value is going to be. So a plus 0.34 plus a 0.76, and we're going to get a voltage of plus 1.1 volts. So this cell is going to be able to do some work for us. It's going to turn on a light bulb. It's going to run our cell phone or our iPod. Now we could also do this as a half-cell method, where we would write each equation as to what's going on with it. And in this particular method, we're saying, okay, zinc is being oxidized. Zinc is going to zinc ions. That's oxidation. We looked the value up on the table, and because we've got it written as oxidation, we had to change the sign of this because now we have the equation written as oxidation and not reduction. So it was a negative 0.76. I had to change it to a plus because we're in an oxidation reaction here. We do the same thing now and say, okay, what's going on in the other half cell? Well, in the other half cell, we've got copper ions going to copper metal, copper ions going to copper metal. And because that's a reduction reaction, we simply take the value straight from the table. We do our overall, and we add these values together, and we get a 1.1 voltage, a plus. So it doesn't matter what method you choose to do. In this method, remember to take your values straight from the table. And in this method here, make sure you change the sign for your oxidation half reaction. All right, so be very careful with that. Let's do a couple more examples. Okay, in this case, we've got the shorthand notation. We've got an aluminum half cell and a zinc half cell, and we're saying, okay, this is shorthand notation, so this is going to have to be my anode. In shorthand notation, this has to be my cathode because it's on the right-hand side. So if you wanted to calculate this, we'll simply say, okay, for the aluminum, we're going to do the half cell method here. Because we've got aluminum going to aluminum ions, this is my oxidation half cell. So I look up the value on the table, and it's a plus 1.66. On the table it would be negative, but I had to change the sign, remember? Okay, so I'm going to put a little arrow here and say sign changed for oxidation. Okay, I do my other half reaction here, and it's going to be zinc ions going to zinc metal, so that's reduction. So I'm going to keep that sign the way it is. Now, you may notice here that we've got a problem. We don't have the same number of electrons, and we know from our balancing of redox equations that we have to have the same number of electrons. So I'm going to try and balance this, and I'm going to say, okay, I got to multiply this top equation by 2. And I'm going to multiply this equation by 3. Now you notice that I haven't done that to my voltages. Okay, and there's a reason for that. If we go back and look at our little diagram of our mountain range here, okay, what we're saying is that 6 electrons are going to go from zinc to my aluminum. And the question would be, well, in this case it's gold, but in any case it could be, we could put aluminum down here or up here or whatever. It doesn't matter how many electrons are falling from zinc to gold. They're falling from the same height, aren't they? It doesn't matter how many we have going. The fact of the matter is, every single one of them is falling from the same height. And in that case, you know, if you're on top of a hill and you have one rock and you throw it down over, that rock hits with a certain velocity. If I throw another one, it's not going to hit with 2 times the velocity, is it? That second rock is going to hit with the exact same velocity that the first one hit. And if I throw the third one, it's going to land with the exact same velocity as the first 2, right? Because they're all falling from the same height. So the amount of voltage you're getting is not going to be 6 times because you have 6 times the electrons. The voltage you get is exactly the same because every single electron is falling from the same height. What you will get is a larger current because you're going to get more electrons flowing for the same time. All right, so you're going to get a greater current because current is like the number of amps that you measure from your battery is going to be greater because you're going to have more electrons flowing for the same amount of time. So the voltage is going to be independent of the number of electrons. So when I rewrite this, I've got my, I've now balanced my equation for electrons, so electrons are going to cross out. And you notice that the voltage stays the same. What kind of E is that? Okay, the voltage is staying the same here. I just done it again. Okay, the voltage stays the same. Because it's independent of the number of electrons. It's dependent on how far they're falling from. Okay, so the voltage of the cell depends on the difference in the electrical potential energy of the half cells and not the number of electrons. So did we have to balance that for electrons? Well, yes. If they wanted you to get the overall balanced equation and determine the voltage, then yeah, you'd have to do this step here to make sure the number of electrons were equivalent, but the voltage is going to be unaffected, okay? Because it doesn't depend on how many electrons. It just determines the distance that they're falling, or in our case, the potential difference between the two half cells. So very important. Okay, here's another one. We want to calculate the E cell for this reaction. And what we're looking at here is we're saying, okay, what's going on here? Well, in this case, the nitrates are definitely going to be spectators, aren't they? So what we have going on is we've got iron going to iron 2+, and we've got nickel ions going to nickel metal. So that's basically the net ionic reaction here. So what we want to be able to do is say, okay, here's a method where we can write the shorthand notation, iron going to iron 2+, separated by our salt bridge, and then nickel going to nickel metal. So this is going to be our anode, so this is going to be the oxidation of iron, and this is going to be our cathode, the reduction of nickel. So we can do this the half cell method if you want, or we can just quickly say, okay, E cell is going to be the cathode minus the anode. Now that we've established what our cathode and anode is, we look up our values from the table. Okay, so this is the value for nickel, straight from the table. This is the value for iron, straight from the table. Careful with this negative sign here. And therefore we get negative 0.26 plus a 0.45, and we get a voltage of 0.19. Okay, so easy enough. Here's another one. The question is saying, well, how do we know which way the electrons are going to go? Is there an easy way for us to determine this without looking at the table for the most part? Now, we can easily look at the table and determine which one is going to be the anode, because the anode is the reaction that's, on the anode side of the table, on the oxidation side of the reduction table, the anode is the one that's lowest. That's the one that's easiest to oxidize. But if we look at this equation, we want to be able to simply say, okay, in this case, we're looking at zinc being oxidized and hydrogen being reduced here to produce hydrogen gas. The important thing that we're looking at here is the idea that the value of the E is going to be positive for anything where the reaction is going to be spontaneous. So because the electrons always flow from zinc to hydrogen, we're saying that that's a spontaneous reaction. As soon as we hook this up, the electrons spontaneously start going in that direction. They never go backwards here. They always go from zinc to the hydrogen half cell. So we would refer to that as a spontaneous chemical reaction. And in this case, every time we do this, if the E cell ends up being a positive value, then that means the electrons are flowing in the direction that we have it written, the anode to the cathode. All right, so if we do a calculation, we can always say that the E cell is going to be positive if the electrons are going to move spontaneously. So, if I'm on top of a hill and I throw a rock out across, the rock is always going to fall down. That's a spontaneous direction because the rock has high potential energy. It's going to lose its potential energy as the rock falls. So same thing's true here. The electrons are always going to go from the half reaction that has the higher potential energy. Okay, so on our table, the cathode is always going to be the higher one than the anode. So the anode is always the electrode that's lower. Okay, and we want to be able to look at this and say, okay, can we make a prediction here? Is electricity going to flow? The way we have it written is it's saying that this guy is going to be the anode, and this guy should be the cathode. So we're saying, are electrons going to flow in that direction? And what we're going to do is we're simply going to say, well, what's the position of cadmium relative to copper? If cadmium is lower, if the anode is lower and the cathode is higher, so if cadmium is lower than copper, we're in business. So let's go look at our table. Where is cadmium located with respect to copper? Well, there's copper right there, and where's cadmium located? Cadmium is right there. So cadmium is lower than copper. So absolutely, the electrons are going to flow from cadmium to the copper. Okay? Is that what we predicted? Yes, the electrons should be flowing from cadmium to copper. Can we prove this? The answer to that is absolutely. We can prove this by calculating E cell. And if we write E cell here, we should be able to calculate this to be a positive value. So when we put the values in, lo and behold, we get a plus 0.74. That's what we predicted. All right? So you can either calculate it, and calculating it, there's no guessing, is it? If you calculate it and it's a plus value, then you know it's spontaneous as written. If you get a negative value, then the electrons are not going to flow as written. So we're predicting electrons to flow that way. And they do. Okay, here's another example. Now this case we're dealing with some other type of anodes and cathodes. So what we're looking at is the idea of iodine and chlorine. If iodine as the anode is lower on the table, on the reducing agent side, then we're in business. So let's go and look up iodine and chlorine. Okay, and I have to move my table up here because chlorine is right there, and where's iodine? Iodine is right there. So in this sense, we're saying electrons should flow from the iodine to the chlorine, or iodide to the chloride, because iodide should be the anode. It's lower on the table. Iodide is easier to oxidize because it's lower. Is it? Well, let's prove it. Okay, so we're making a prediction here that if I minus is lower, then it should be spontaneous. We do our calculation. Lo and behold, we're saying that, yep, indeed, it's positive, so electrons are going to flow in that direction. Okay. Here's a table, here's a question, public exam question, multiple choice. And what it's saying is, okay, the question in black there says, which will react spontaneously with bromine but not with iodine? And our four choices are given here, multiple choice. So what I want to do is I'm going to look at this, and I have to logically look at this and go down through it and say, okay, if I've got bromine and iodine, that's all I've got. I don't have anything else there. And I'm saying, okay, well, what's going to happen to bromine? Well, bromine is going to have to be reduced, isn't it? So Br2 is going to have to somehow collect electrons to produce Br minus. And at the same time, in another test tube, we're saying, okay, iodine is also going to have to be reduced. So what we're saying then is we want something that's going to react with bromine but not iodine. So in terms of positioning on the table, if this is going to be the cathode, the anode has to be lower, or the cathode has to be higher. So what I want to do is I'm going to look at each of these. I'm going to look at fluoride first, because fluoride is only on the table in one location. If I look at the positioning of fluoride relative to bromine and iodine, you guys can check your table. What you're going to find is that the fluoride equation is above both of them. And in this case, the fluoride is going to be wanting to give up its electrons so that bromine and iodine can pick them up. Now remember what we said about fluoride? Because it's so high on the table, fluoride ions, once they have that extra electron, buddy, I tell you, they're not going to give them up. And they're not going to give them up to bromine, and for sure they're not going to give them up to iodide, because it's much more stable for fluoride to stay in this form than it is to give up its electron to be in this form. So that fluoride is stable. It's not going to want to give up its electrons. So because as an anode, that value is going to say it's going to be non-spontaneous for both of these, because it's above both bromide and iodide. And if we could calculate this, I'm simply going to show you the calculation for bromine. I'm going to do the calculation bromine as the cathode and fluoride as the anode. It works out to be a negative 1.8. It's a negative value. You can do the exact same calculation for fluoride and iodide, and you're going to get a negative value, right? Because fluoride just does not want to react. So it's going to be non-spontaneous for both. Okay, let's look at the other examples. Now, if you look at chromium on your table, chromium can be found on your table in two locations. All right, let me just find it here for you. Chromium can be found in two locations here. and it can be found, okay, right here, and it can also be found way down further, right here. Okay, so let me put chromium on your table there in 2 locations. So chromium is found there twice, but in this form, chromium has to be reduced, because that's what we have in the test tube, chromium ions. So we either reduce chromium ions, or in this reaction up here, we would oxidize it by reversing this. So how is it we want chromium to behave? Well, let's go back. How do we want chromium to behave? We need chromium to behave as an anode, because the bromine and iodine need to be reduced. So the chromium has to be the anode, so the chromium has to be oxidized. Its position relative to iodine and bromine is going to be way below them. All right, so let's just go back to our table. We're looking at this chromium right here. We want the chromium that's going to be oxidized. And you can see that it's way down below in the iodine. Bromine is way up here now. So its position, the chromium is way below the iodide and the bromine. So what we're saying here is, hey, because this is lower, that electrons are definitely going to flow in that direction. Woo, woo, right? So chromium 2+, because it's lower than iodine and lower than bromine, should be spontaneous for both of them. All right? So chromium, as being oxidized, is lower than both of them, so therefore we should see the electrons moving. And if you want to do the calculation for these as chromium as the anode, and each of these as a cathode, you'll find that both of these are going to end up being a positive value. Give it a try. They should both end up being positive. Okay? Let's look at the other one. Iron 2+, once again, iron 2+ is on your table in 2 locations. And we want the iron 2+ that's going to be oxidized, because the bromine and iodine need to be reduced. So the iron that's being oxidized is this one, iron 2+, giving up its electron to make iron 3. Now, looking at its position, because it's below the bromine, it's definitely going to give up its electrons to bromine because it's lower. It's easier to oxidize. That's good for bromine, because bromine's now going to pick up those electrons that iron is going to give up. In the case of iodine, iron is more stable than the iodide ion. So iron is not going to give up its electrons to iodine, because iron is the easiest thing that is harder to oxidize than this. So the 2I- would be easier to oxidize. We don't have that, so this reaction is definitely not going to happen. So iron 2+ will be spontaneous for bromine, and it's going to give a positive E cell. You can do the calculation. But it's going to be non-spontaneous for iodine, because it's going to give me a negative value. It's lower on the table. Okay? So there we go. So the answer to this multiple choice, spontaneous for bromine, non-spontaneous for iodine. So the answer is C. And in the case of manganese 2+, once again, manganese 2+ is found twice on your table. We need to be able to see Mn2+ being oxidized, because it needs to act as an anode. And where we find it is up here on your table above the bromine. It's the manganese oxidizing to give up its electrons to produce MnO2. And you'll see that that's not going to happen. Manganese 2+ is not chemically reactive enough. It's too hard to oxidize. Bromine and iodine are not capable of causing that oxidation. They're too weak. All right? These guys are too weak. So therefore, it's going to be non-spontaneous for both. And if you wanted to calculate this, you'll find that both of these are going to be negative E cells. Okay, so there you go. So on the test, you can see that which one is going to be spontaneous for one but not the other? It's the one that's between them. These two are spontaneous for both, or sorry, non-spontaneous. They're not going to react because they're above both of them. This is going to be spontaneous for both of them because it's below both of them. So you can logically go down through there. And again, calculate the E cells in each case to prove to yourself that only the ones that are positive E cells are going to be the ones that are spontaneous. Okay, here's another one. We're looking at this reaction and we're saying, okay, this is showing us having Gold 3 plus going to gold solid. The value is plus 1.5. This is going to be my cathode. The other chemical reaction here is going to be hydroxide going to oxygen and water. And the E cell here works out to be 0.110. And again, we're looking at this and saying, hold on now, we got odd number of electrons. Doesn't matter, does it? It does not matter that we have odd number of electrons. However, if they wanted us to balance this for the number of electrons, then I'd have to multiply this guy by 4, this guy by 3, but I do not multiply the voltages. Okay, and when I work this out, of course, it's going to be spontaneous as written, and there we go, the anode cathode shorthand notation. Spontaneous as written because it's positive, but it does not depend on how many electrons are moving, independent of electrons. Okay, one last question. In this particular question, they're saying, okay, well, what happens if I give you a combination that's not on your table? But when I hook it up, I get a voltage reading coming out of my voltmeter. Can I determine the half-cell reduction value for that cell right there? And the answer is, yeah, why not? We know what the E cell is. We know what the anode is because we can get that from the table. So I'm looking at this and we're saying, okay, E of the cell is E cathode minus E anode. I know what E cell is. It's plus 1.75 volts. And I know what my anode is. Anode is right from the table for zinc. It's a negative 0.76. Okay, I solve this. Okay, the very first thing I've done here is I tried to take care of this sign, change that to positive, and now I'm simply going to take that over there and I'm going to solve for my E of the cathode. So there we go. So E of the cathode is 1.75 minus 0.76, and we're going to get a value of a plus 0.99. So what we can do now is we can write our reduction equation for palladium. There it is, palladium plus 2 electrons. It's a plus 0.99. Now we can put that in on our table. Okay, there we go. So we got that one ranked. Now we know exactly where that one shows up on our table. Plus 0.999. Palladium would end up being somewhere around where? Right in here somewhere. Okay, so reduction table, you get this on your periodic, on your public exam, all right, just as it is without the writing that I have there. I put the writing in because I just want you guys to be able to see what's going on there. So mark it up, get some ideas. When you go to study this, you got some ideas here. Okay, I'm going to stop there. Go look at some of the public exam questions here. Multiple choice questions show up a lot with these types of questions, or they could also get you to, balance the half-cell reaction and get the voltage. And these questions where they try and get you to logically go down through and pick which one it's going to be from the table, you can do that. But again, if you can't do the logic thing here about the positioning, then by all means do the calculation and look for the ones, negative is non-spontaneous, positive is spontaneous. I'm going to stop there now and check out some of the textbook questions here, and by all means go get some public exams and look at some of the questions. Fire some of these off to your online tutor if you have some trouble. All right, see ya. Bye-bye.